Assalamu alaikum. Welcome to the next class. In this class, we'll be discussing the fault analysis using the Zbus. We have done a lot on the fault analysis by uh, in previous chapters, and that was by the usual manner, but it is slightly different. And we have assumed in that case the number of buses to be limited to 2, 3, or 4. But when the number of buses in a power system increases, it is very difficult to analyze the power system in the manner which we have discussed earlier. So for a power system where the number of buses is very large, so Zbus technique provides a useful tool in analyzing that type of power system. So to perform the fault analysis using Zbus, we need to first form the Zbus. There are usually three methods of calculating Zbus. One is first actually simply taking the inverse of the Y bus, which we have calculated in the load flow analysis. The second one is the current injection method, and the third one is the Zbus building algorithm. So we'll be discussing one by one. Let us first take the Zbus, which is actually the inverse of the Y bus. We know that from the load flow analysis, this II is equal to summation J is equal to 1 to N Yij Vj, where II is the injected current at the bus, and Vj is the jth bus voltage. So Vj over here. If we have Vi, that means the ith bus voltage. So expanding this, we get II is equal to V1 Yi1 plus V2 Yi2 plus this up to Vn Yi. Actually, I expanded this. Now, giving the I different value, here I will be equal to 1, 2, or n for n bus system. So when I is equal to 1, the equation becomes this. When I is equal to 2, the equation becomes this. When I is equal to n, the equation becomes this one. So it has been then represented by this, where this is Y bus, this is V, and this is I. And the order of this is n cross 1 for n bus system, this is n cross n, and this is n cross 1. Now I can first write the right hand side on the left hand side of the equation, and then I. Taking the inverse of this Y bus and multiplying it over here and here, we get V is equal to Y bus inverse into I, where this Y bus inverse, when we take, I will represent it by Z bus into I, where the Z bus is equal to Y bus inverse. This is actually what we have started at the beginning of this topic, that Z bus should be, we can calculate it from the inverse of the Y bus. And from here you can see V is equal to some, let us say we have just named it Z bus. It is because when current is multiplied by something and it gives voltage, it means this has to be the dimensions of the impedance. So that's why it is known as Z bus. Here, all the elements of this Z bus will have the dimensions of the impedance. It is because, as I have told you, whenever anything is multiplied by the current and it gives the voltage, dimension of voltage, that means the dimensions of this anything or this constant should have to be impedance. So it will be impedance. That's why it is known as Z bus. One more thing, one important thing is that I have written the Z bus like this: V1, V2 up to Vn. Its order will be n cross 1, and I have expanded the Z bus, that is Z11, Z12 up to Zn. It will be similar to that of Y11, Y12 up to Yn, but here we have written it on this side, on the current side, and it will be Z named as Z. Z21, Z22 up to Z2n, Zn1, Zn2 up to Zn. Its dimensions will again be n cross n. So current vector, it will be again n plus 1. So if you simplify it like this, that is V1 is equal to Z11 I1, Z12 I2, Z13 I3, that is up to Z1n In. So first equation will be this. Second equation for V2 will be Z21 I1, Z22 I2, Z23 I3, that is up to Z2n In. So this will be the V2. For Vn, it will be like this. So all these equations can be written in a single equation in terms of I, where I can vary from 1, 2 up to n, that is Vi is equal to Zi1, I1, Zi2, I2 plus up to Zin, In. And in terms of summation term, It can be written like this: Vi is equal to summation j is equal to 1 to n ij z ij. This is again an important result because it is similar. It is similar to this equation. I just transform this equation into this equation. You can see it over here. Here it was I is equal to summation Yij Vj. Here it is Vi is equal to summation Ii Zij. Sorry, Ij Zij. So it is because this equation is very important. Like this equation in case of Zbus is very important because it is this equation which helps us to find out the Zbus. That's why I derived this equation from this Zbus. Now, what are the properties of the Zbus? First, the size of the Zbus will be same as that of the Zbus will be same as that of the Zbus. That will be n cross n for an n bus system. It will be again a symmetric matrix provided Zbus is symmetric, and we know that Zbus is symmetric when there is no tap changing transformer. If there is tap changing transformer, then Zbus will not be symmetric, and hence Zbus will also not be symmetric. It is a full matrix. We know that the Zbus is a sparse matrix, but here it is full matrix. It does not. We cannot say it is sparsity very high. We can say it is sparsity very low. Usually it is full matrix. There is in most of the cases all the elements will be non-zero elements. That's why it is full matrix. Now the second method is current injection method. Now what is this? You might have done a bit in your previous classes, that basic electrical engineering. When we calculate the Thevenin impedance across any network, what we do, we simply deactivated all the sources and then put a voltage source or a current source at any point where we have to calculate the Thevenin impedance and then calculate the voltage if current source is used or current if voltage source is used. And taking the ratio of voltage to current, at that point we can get the value of the impedance, Thevenin impedance or Norton impedance at that point. Similarly, here what we do in this case, a current source is injected at the ith bus and all other sources are deactivated. The elements of the ith column of the Z bus can be then calculated. Here slightly more elements are calculated as compared to the earlier one, but the procedure is same. All the active sources, they are deactivated, and then all the sources are deactivated and a current source is injected at any particular bus. Let us say it's a ith bus, and then the bus voltages are calculated, which gets produced because of this current source which is injected at the ith bus, and the ratio of these voltages divided by this current source will get us the ith column of the Z bus. So I will let you know how to do this. This step is repeated for all other buses to calculate the other columns of the Z bus, because just wait, I will let you know what does this mean. We know this equation, I have written it again. So Vi is equal to summation j is equal to 1 to n Zij, and it is equal to Zi1 plus Zi2 plus dash Zi, that is when j is equal to I plus dash up to plus Zin. Now when all other currents are zero, let us say only the I1 current, we are injected a current at bus 1, and all other currents, injected current at other bus are zero. So in that case, this Zi1 will be equal to Vi divided by I1. When I is equal to 1, we get V1 by I1, that is Z11. When I is equal to 2, we get, that is because we have to calculate voltage in I1. It is known to us when we inject the current. We are actually injecting a known current. So we'll calculate all the voltage. That means Z11 will be equal to V1 by I1. So Z21 will be equal to V2 by I2. V2 by I1. Z31 will be equal to V3 by I1. So in that case, we can calculate the first column. This, when I1 is introduced, we can calculate the first column of the Z bus. So Zii, in case of when this when the current source is injected at the ith bus, that is II. So in that case, Zii will be equal to Vi by Ii. That is, all the ij's will be equal to 0. This is what we have done earlier for calculating the Norton equivalent. All other currents except I is equal to 0. Let us take an example of 3-bus system. This is bus 1, this is bus 2, this is bus 3. We are injecting the current I1 at bus 1. So by injecting the current source at bus 1, we will calculate V1, V2 and V3. We will calculate V1, V2 and V3. Simply V1 will be equal to this I1 multiplied by impedance seen by this. This impedance will be, since this is not connected to ground, one of them has to be connected to ground, so that we may have the this closed path. Let us say this is connected to ground, then this plus this will be in series, and then the combination this will be in parallel. That will be the total impedance seen by this. So the voltage at this point will be equal to I1 into that impedance. So it will give us at that time Z11. So from here, Vi is equal to Zi1 I1 plus Zi2 I2 plus Zi3 I3. We have to first, because in this case I1 and I2 and I3 is 0. So Vi is equal to Zi1 I1. Now I can be equal to 1, 2 and 3 because we can calculate V1, V2 and V3. So here V2 can be simply calculated. We have just calculated V1. V2 will be equal to this V1 minus the voltage drop across this transmission line. So we have to calculate this uh, current by the current divider rule. It will be equal to this total impedance divided by the sum of the two impedances multiplied by this I1 will be the total current in this. So this voltage will be equal to then this V1 minus the voltage drop across this. Similarly, we can calculate the V3. When we have calculated all these voltages, so Z11 will be equal to this V1 by I1, Z21 will be equal to V2 by I1, and Z31 will be equal to V3 by I1. That has been replaced over here. So V1 when I is equal to 1 will be equal to Z11 I1. So Z11 will be equal to V1 by I1. Similarly, Z21 when I is equal to 2. That means when we calculated voltage at bus 3, Z21 will be equal to V2 by I1. Similarly, Z31 will be equal to V3 by I1. So here we have calculated Z11, Z21, Z31. That is the column of this Zbus. By similarly placing this current source at this, that is I2 at this, we can calculate then this column, and by placing a current source at this and deactivating other current source at other buses, we can calculate this column of the Zbus. So by this method, this is how we can use this method to calculate the Zbus. So the next one is the Zbus building algorithm. So in this case, it is a step-by-step programmable technique which proceeds branch by branch. In this case, what we are doing, we are adding branch by branch the buses and then calculate the Zbus. So its advantage is that any modification of a network does not require rebuilding of Zbus. Whenever there is a modification of the Zbus, we need not to require to recalculate the whole Zbus. We just have to use this modification which we are going to discuss, so that our time is not wasted in recalculating the Zbus. Now when it is branch by branch method, that means we are adding branch by branch. So adding branch, uh, you can see adding branch, we have four situations in that case. That is, we can add branch between a new bus and a reference bus. We can add a branch between old bus and a reference bus. We can add a branch between old two buses, or we can add a branch between old bus and new bus. So there are four modifications depending upon the situation which are available. Upon adding a new branch, four situations may be present, and based on the situation, four modifications are done. So on these situations, whether the branch is added between old bus, new bus, old bus, new bus, reference bus, or between old buses, we have four modifications. The first modification is when this branch having an impedance of Z bus is added between a new bus and a reference bus. So let us say this is our power system and it has n buses, and new bus we are assuming to be the kth bus, and R is denoted for the reference bus. and I have taken all the connections of the buses outside, and I have shown all my power system in the box. So since we are only concerned with the nodes or connections to the bus, I have taken them out like this. So let us say this is 1, 2, 3, and in between we have ith bus, and in between we have the jth bus, and then I, and finally we have a reference bus. So it is connected like this, and we are assuming always to be always at the buses that the currents are to be injected. That's why the current direction will be like this. When it is connected like this, you can see that Vk, that is the voltage at this bus, that is the new bus which is connected, new bus, between this and reference bus, Zb is connected. So Vk will be equal to Zb into Ik, Zb into Ik. And we know that before adding uh, the kth bus, Vi is equal to I1 Zi1 plus I2 Zi2 plus Zin In. This actually summation of j is equal to 1 to Nij Zij. I have expanded it. So when we introduce this Zik, Vi will be equal to Zi1 I1 plus Zi2 I2 plus Zin In plus Zik because now there will be one more bus and that contributed to this system as Ik. Now this Vi is the voltage of the buses from 1 to N, when N is equal to 1 to this. For this case we have introduced K also, but will not actually will not give. Okay, let us take K also because here there are now N plus 1 buses including N buses. So this I can vary. Actually I will have, since this is the voltage of the kth bus which I have taken separately. Okay, let us see that this also includes that bus, but usually we use these equations to exclude the kth bus, but I have here included the kth bus as well. Now for this case, you can see that this Ik has nothing to do with the currents in between these voltages. So I will come to this. Just I will add this sentence to uh, here, that this Ik is simply going from the kth bus to the reference bus. It has nothing to do with the currents, or we can say it is not modifying the currents that is injected at the other buses. Now when I is equal to K, I will use the same equation. You can see it here. When I is equal to K, Vk is equal to Zk1 I1 plus Zk2 I2 plus Zkn In plus Zkk Ik. But what is the value of K1? Actual Vk, sorry, Vk is equal to Zb Ik. That means comparing equation 1 and 3, that means this has to be equal to 0, Zk2 has to be equal to 0, Zk3 has to be equal to Zkn has to be equal to 0, and this Zb has to be equal to Zkk. That is this Zb has to be equal to Zkk. That means when I represent in general form, that is Zki is equal to 0, since our system is, we're assuming the system to be symmetric, Zik will also be equal to 0. That's why I have taken that this Zik will be equal to 0 here for any I is equal to 1 to N, excluding K now. So because it will give us actually the row of the Z bus, this Vi, when v is equal to 1, I is equal to 1, Z11 I1 plus Zi2 I2 plus Z1N In plus, let us say it is Z1K Ik. Since there is no Z1K or Z1K is equal to 0, so Zik will also be equal to 0. So having these two equations, that is this equation into consideration and this equation into consideration, you can get Z old will be equal to Z new bus will be equal to, one is the Z old, and here it will be the column of 0, and we have to add here column of, sorry, row of 0, and at kth place we have to add the, that is this Zp will be equal to Zkk, because this will be the kth row. This will be first row, second row, third row, fourth row, fifth row, let's say nth row. And we know that the last element, that is this Zik, for all the rows from I is equal to 1 to n will be equal to 0. And for the kth row, that equation is given by this. And for this, Zk1 is 0, Zk2 is 0, Zk3 is 0. That means this comes out to be 0, and finally zkk will be equal to zb. And in this way we have calculated the Zbus. So we don't have, after deriving this, we don't have to do this type of the equations, writing equations. What we have to do, whenever an impedance is connected between a new bus and a reference bus, we have to put the old bus over here, put a column of 0 over here, put a column of 0 over here, and the dimension of this column will be equal to, this will be equal to 1 cross n, this will be equal to n cross 1, and here, since this will be only one element, it will be equal to ZB. So here we have to put the old Z bus. Again, the order of the new bus, since we are using new Z bus, since we are using a new bus, the KS bus, we are adding a bus, so it will be n cross 1, n plus 1 cross n plus 1, because the order of this will be n into n, order of this will be n cross 1, order of this will be 1 cross n, the total will be n cross 1 into n cross 1. Sorry, n plus 1 cross n plus 1. Now the type 2 modification is that ZB is added between a bus and the old bus, new bus and old bus. So this is the new bus, this is the old bus, and we are connecting ZB, and we are assuming a current IK to be injected in the bus, and the total current injected in the bus will be now II plus IK. So from here, this VK will be equal to VI dash plus IK ZB. I have written here VI dash because this VI will be now modified because of the presence of this branch. So earlier it was VI, now it will be VI dash. We'll see what is this VI dash and what is VI. So VI dash will be now ZI1, which actually is the summation of j is equal to 1 to n ZIJIA. I am expanding it, it's an expanded form. That is ZI1 I1 plus ZI2 I2 plus ZII when j is equal to II plus IK, because at the ith bus we have the summation of the two currents II plus IK. Here it is II and here comes the IK. They are added over here. So at the ith bus, the current is not II only, it is II plus IK plus dash 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 ZIN IN. So here K is included because we are here trying to calculate the rows of the Z bus, but excluding the kth row. We'll derive the kth row separately. So here Vi dash will be like this. So I can represent it in terms of the summation excluding this term. So it will be equal to, because here j is equal to I. So summation j is equal to 1 to n, but j is not equal to I because I am excluding the ith term. Zij plus Zii plus Zii So these two terms actually is the Zii plus Zii Now I can include this to this summation. I will get summation j is equal to 1 to n Zij plus Zii Now you can see this is actually the Vi that I have told you now. This Vi dash has changed from Vi to Vi dash. It is because of the additional term of this. So Vi dash will be equal to summation j is equal to 1 to n Zij j plus Zii Ik. So I can write it as like this. Vk is equal to Vi dash plus Ik Zb, which is this Vi dash Ik Zb. But Vi dash is equal to now this is Vi plus Zii Ik. So I can write it as Vi plus Zii Ik plus Zb into Ik, because this comes out from this Vi dash. So Vk is equal to Vi plus Zii plus Zb plus into Ik. Vk is equal to, this is summation j is equal to 1 to n Zij plus Zii plus Zb into Ik. So Vk, this is the kth row, Zi1 I1 plus Zi2 I2 plus Zin In plus Zii plus Zb into Ik. This gives us the kth row. That is, I will write it as like this. This is Zi1, Zi2, there is Zin. Then the last one will be Zii plus Zb. That is the ith row. I will let you know. From this point to this point, it is nothing but the ith row of the old bus. Ith row of the old bus. So whenever a ZB is connected between the old bus and the new bus and the old bus, it is as good we are expanding our Z bus by placing the ith row of the old bus as the kth row. But definitely one element less. The last element will be Zii plus Zb. Now let us try to derive the column of this, because in that case this is the kth row equation. Now we have to see other voltages, from that we can get the column of the this matrix. Now let's say I is equal to 2 from here. Where it is here, because here we have taken I is equal to k and we are getting the k. So let's say I is equal to 2, so it will be equal to, we can have I is equal to 1 as well. I is equal to 2 is equal to Z21 I1 plus Z22 I2 plus Z2 I plus IK, because at ith bus we have two currents plus Zn Z2 and In. So taking this Z2 IK separately, making it an another term of corresponding to IK. So it will be equal to V2 is equal to Z21 I1 plus Z22 I2 plus Z2 I. This is equal to I plus Z2 and In plus Z2 IK. Now I have taken this separate. Similarly, V3 is equal to the same earlier equation plus Z3 IK. Vn is equal to the same equation plus Zni IK. Now this will introduce a column in the new bus, and this is the kth row which we have already discussed. That is this. You can see for the Z bus now we have the additional column, and the column is corresponds to Z2i, Z3i, Zni. That is Z first. For the first row it will be Z1i. Z1i, Z2i dash plus Zni, and the last value of this column will be Zi plus Zb. So in nutshell, whenever a ZB is added between the new bus and the old bus, what we have to do, we have to place an old bus over here whose dimensions are n cross n, and the row will be, this row will be the ith row of the old bus of order 1 cross n, and this column will be the ith column of the old bus, again n cross 1. So the last term will be equal to Zii plus Zb. So we don't have to use any calculations here. We just have to use an old bus over here, ith bus column here, ith bus row here, and then Zii plus Zb, because all these are known. And there you can see it is very simple. Again, the order of the new bus will be n cross 1 into n cross 1, because we are adding a new bus. Now the next modification is the type 3 modification. In this case, Zb is connected between an old bus and a reference bus. So it is like this. We have an old bus and we have a reference. Again, we are assuming that a current to be injected over here. So this here, the current by the I is injected II. Now another current is injected IK. So the current here will be II plus IK. So we first introduce a new bus. Let us say we have connected a new bus K here, and ZB is connected between that bus K and this I, which we already just discussed. And ZB is connected between I and K. It will be reduced to type 2 modification. And we know that for type 2 modification, we have this type of the matrix. So we can get Z old, Z new like this. The relation of the V and I in case of the type 2 modification will be like this. That is, Vk will be equal to Vi dash plus IkZb, Vi plus Zii plus Zb into Ik, which we have already discussed. So Vk is equal to Vi plus this. Now we will connect this kth bus to the reference bus, or short circuit the kth bus to R bus. So in that case, this Vk will be equal to 0. When Vk is equal to 0, from equation 8, we'll put this Vk is equal to 0 over here, and I can get Ik. Ik is equal to minus Vi by Zi by Zb. So Ik will be equal to summation j is equal to 1 to n Zij Vj divided by Zii plus Zb. This is the equation 10, which is the important equation, and from this equation we can get the Z bus. So V1 is equal to Z11 I1 plus Z12 I2 plus Z1i II plus Ik plus Z1n In. This is V1. So because here at ith bus we have two currents, I will separate it out like this. This is Z1i Ik, because it comes out from here. So I will replace it, and I will replace it as m. So Vm will be equal to Zm1 I1 plus Zm2 I2. Here I am replacing this by m, because this will be m I1, m this will be m Zmi II plus Zmm plus this Zmi Ik. This is the last term. So Vm will be equal to summation j is equal to 1 to n Zmj Ij plus Zmi Ik. Here I usually earlier I was representing the different voltages as I voltage is Vi. Since we are fixing the bus as bus I is the bus where we have connected the Zb, so I can vary these bus by using another subscript m instead of I, because if I here use I as a this subscript, it may get confused. That's why I have written over as m. So Vm is equal to summation j is equal to 1 to n Zmj Ij plus Zmi Ik. I'll stop here. I will continue in the next class.